In this video, we shall look at a couple of problems associated with Gauss's law. The first problem involves concentric charged spheres, and the second problem is associated with coaxial charged long cylinders. The following problem is associated with concentric charged spheres. Inner shell has a total charge of plus 2q, so that is the inner shell with inner radius of A and outer radius of B. So the charge on it is plus 2q. The outer shell has a charge plus 4q, so that is the outer shell with inner radius C and outer radius D. And the charge it contains is plus 4q. Find the electric field in terms of capital Q at the following distances. R less than A, meaning in this region. R between A and B, that means in that region. R between B and C, in this region. R between C and D, that means in this region. And R is greater than D, that means that region. Let's first determine the charge distributions on the surfaces. Let's look at the inner shell. Now we know inner shell carries a total charge of plus 2q. How does this plus 2q distribute it in that inner shell? That is the question. The plus 2q on the inner shell is confined entirely on the outer surface, like that. So the inner shell's charge is entirely on the outer surface. Now, this inner surface of the inner shell carries no charge. Also, there should not be any charge within the shell, within that inner shell, because we are referring to an electrostatic condition, and under an electrostatic condition, charges cannot exist within a conductor. Now let's look at the outer shell. We know it has a total charge of plus 4q. How is that plus 4q distributed? Now the inner shell has a charge plus 2q. So this plus 2q will induce an equal amount but opposite sign charge on the inner surface of the outer shell. So that means the inner surface of the outer shell will contain a total charge of minus 2q. Since the total amount of charge of the outer shell is plus 4q, then the outer surface of the outer shell must contain positive 6q, because only then plus 6q plus minus 2q will be plus 4q. Now we are ready to find electric fields at different distances. So let's start with R less than A. Let's construct a Gaussian surface for that distance. The Gaussian surface for R less than A would look like that. So it's a spherical surface with radius R. Now note that particular Gaussian surface, this one right here that we have just sketched, has no net charge within it. So that means the net charge within that Gaussian surface is 0. That indicates there is no electric flux through that surface. And the obvious conclusion is the electric field at that distance must also be 0. So at any point on that Gaussian surface, the electric field is 0 for the reason that we have just mentioned. Now let's look at the second region. R is between A and B. So between A and B, that means within that inner shell. So a typical Gaussian surface within that region will look something like that. At a distance R, let's say. And we also see, as in part 1, there is no charge enclosed by this Gaussian surface. So the net charge enclosed by that Gaussian surface is 0. And using the same conclusion, the electric field there must also be 0. Part 3, R between B and C. So R between B and C is this region right here. So let's sketch the Gaussian surface. like that. And the distance is, let's say, r, somewhere there. Now let's write down Gauss's law for that Gaussian surface. Now we know the amount of net charge enclosed by that Gaussian surface is actually plus 2q. That is this charge right there. So the field from positive charge is, of course, will head in an outward direction like that. And we can write down Gauss's law in a following manner. E at distance r times the area of that spherical surface, spherical Gaussian surface with radius r, is 4 pi r squared. Net charge is plus 2q over epsilon naught. And you can solve for the electric field within that region, and will turn out to be q over 2 pi epsilon naught r squared. And that is the answer for part 3. Now part 4, in the region between C and D. Now C and D region means that. So the Gaussian surface is represented by that dashed sphere. And let's assume that radius is r. And we follow the same strategy as we followed before. Now we note that the amount of net charge enclosed by this Gaussian surface is 2q plus minus 2q. So that means the net charge enclosed by that Gaussian surface is 0. And it follows the electric field at that distance within that region must also be 0. Now part 5, r is greater than d. R greater than d refers region outside both the shells. So something like shown by that dotted surface, the radius is r. So obviously the net charge enclosed by that Gaussian surface is 6q plus 2q, that is 8q, 8q plus minus 2q, and that's going to be 6q. So the electric flux is given by E at that distance. We know the electric field at that distance will be going outward like that due to the positive net charge. So the electric flux is 4 pi r squared times the electric field at that distance. Net charge is 6q over epsilon naught. So the field, the electric field at that distance in that region is quite simply 3q over 2 pi epsilon naught r squared. And that solves the problem. The second problem is associated with a coaxial cylinders in the form of cable. A long coaxial cable consists of inner cylindrical conductor, that's this one, with a radius a, and an outer coaxial cylinder, that's this one, with inner radius b and outer radius c. So that's the inner radius and that's the outer radius. The outer cylinder has no net charge, which means that cylinder right there has 0 net charge. The inner cylinder has a uniform positive charge lambda per unit length. So that's this central inner cylindrical conductor. So we shall simply write the charge per unit length as plus lambda. So what that plus lambda means, within a length, let's say L, of that middle cylinder, there should be an amount of charge that's equivalent to lambda times L in the unit of Coulomb. That's what it means. Find the electric field at any point between the cylinders at distance r from the axis. So which means that point right there, that region right there, and also at any point outside the outer cylinder, the region there. Let's first determine the charge distribution. Now this plus charge on the surface of the inner cylinder will induce a negative charge on the inner surface of the outer cable. So along that surface, there will be a charge per unit length of minus lambda. Since the outer cylinder has no net charge, the outer surface of that outer cylinder must carry a plus lambda, so that when you add this to that, you get a 0 net charge. It must be remembered this is a long cable, long coaxial cable, so the length goes up and down to infinity. So let's keep that in mind, although the drawing just shows a cross-sectional view of it. Let's sketch the Gaussian surface for part 1. The Gaussian surface is a long cylinder like that in the region between the two cylinders. So that's the Gaussian surface. Now note that the electric field is going like that, perpendicular to the curved surface of that cylinder. So the top flat surface has no electric field penetrating through it. So for part 1, the net charge enclosed by that Gaussian surface is given by the positive charge per unit length times the total length of that cylinder, which let's take that to be capital L. So the flux through this curved surface is quite simply the electric field at that point times the area of that curved surface. The area of a curved surface of a cylinder is given by 2 pi r, where the r is the radius of that cylinder, times the length of the cylinder, equals to the net charge. Now we know it's lambda L over epsilon naught. So this is Gauss's law that we are applying. We see that L goes away, and we can solve for the electric field in that region. It will be lambda over 2 pi epsilon naught r. The direction of the electric field is outward from the middle cylinder within that region. Part 2, at any point outside the outer cylinder. So the Gaussian surface will be that big cylinder with infinite length like that with radius r. So we are trying to determine the field, for example, at this point. The net charge that giant Gaussian surface contains is plus lambda minus lambda, so that's 0, but do not forget that plus lambda. So the net charge is given by plus lambda times capital L, which is the length of that cylindrical Gaussian surface. And as before, due to that positive net charge, the electric field will penetrate the curved surface of the cylinder in a 90-degree manner, and the electric field through that surface is given by the field at that point times the area of the curved surface, which is 2 pi r. R is the radius of that cylinder times the length of the cylinder. And according to Gauss's law, this electric flux must be the same as net charge, which is plus lambda times L over epsilon naught. So you see again, the length cancels, and you can solve for the electric field. And it's going to be lambda over 2 pi epsilon naught r. And of course the direction of the field, as indicated here, is in an outward direction. And that solves the problem. If you find this video useful, please don't forget to like, share, and subscribe for notifications on further videos. Thanks for watching.